Good afternoon, everyone. So today our session is on the behavioral modeling and the procedural blocks. Okay, so we will try to understand this behavioral modeling and the procedural blocks. So the behavioral modeling is the highest abstraction level. Okay, so the behavioral modeling is the highest abstraction level in Verilog HTL. Instead of describing the gates or Boolean equation, we describe how the hardware behaves. Okay, so that is what it is in the highly abstraction, the highest abstraction, and we describe how the hardware is going to behave. So the simulator executes statements in procedural blocks to model the intended functionalities. The examples: counters, finite state machines, registers, arithmetic logic units, controllers, protocol engines. These all are some examples of where you can use behavioral modeling in this. So the modeling style, we went and looked into gate level data flow. This connect the logic gates and it uses the Boolean expression. This behavioral modeling, it describes the behavior using the procedural statements. So here we have, so in the continuous, I mean data flow is the continuous where we use the assign statement. Likewise, in the behavioral model, we will be using the procedural statements. So there is a switch level modeling, but we will not go much deep inside it. It is a transistor model. By using the transistor level, we will go and model it. Okay. So exactly, if you talk about the behavioral modeling, exactly if we talk about the behavioral modeling, instead of writing assign y equal to a and of b, okay, we can use, okay, and always it is a procedural block, always block at and this symbol, and begin and end you can have a multiple statements. Okay, so this is the thing where you can write like this. To write like this, the focus is on what the circuit should do, not how gates are connected. So here the focus is what the circuits can do. Apart from that, what are the gates connected? That is the thing. Okay. So in the behavioral modeling, it uses mainly two procedural blocks. There are the blocks, okay, if, else, repeat, forever, okay, and then case. There are initial block and always block. Initial block is non-synthesizable. It is for simulation only. Always is for an uh, is synthesizable. So initial, and we have a begin and end, we can have a many statements. Always begin and end, we can have statements. Okay. The initial block, the purpose is it executes only once at simulation start. Okay. So used mainly in test benches and memory initialization and simulation setup. For this purpose, we will go and use this initial block. So the execution timeline means simulation start, execute the initial block, complete, that's all, runs once and stops. It will run once and it will stop. Likewise, you can have multiple initial blocks are allowed. Initial begin one end and another initial begin. Both will start at a time 0. Both will start at time 0. That is what this block. So initial block uses the test bench stimuluses. Okay, initial, begin, and then these things. And in the memory initialization, initial will begin, read from memory H, and to the memory block we go on initialize the things. Okay, so these are some examples of using the initial block, one of the procedural block. Now always block. Purpose. Executes repeatedly whenever its triggering condition occurs. So whenever a triggering is something, triggering in the sense the input is something, it's got an input where there is a change in input or select line. In such kind of situation, it goes and trigger the conditions. So the general form is always, and you have to use at, and then within the parentheses we will give the sensitivity list. That is nothing but our inputs, our logics. Okay. And then we have to use begin statement if we have multiple statements. Okay. So whenever a trigger happen, it will wait for trigger. It will execute, the statement should get executed and return to waiting state. Okay, then again it will wait, and whenever the trigger happens, it execute. It is not like initial block which will go and execute only once. No, it repeats forever. It is repeating forever. The sensitivity list defines when the block executes. Okay, so if you use ARB, that means the trigger when A changes and B changes. This block will trigger when A or B changes. In the combinational logic, we prefer this wildcard symbol. Asterisk includes all the things. So whatever the thing it changes, it goes. Automatically include all RHS signals in sensitivity list. All right hand signal is included. That is what the this star indicates in the combinational logic block. In the sequential logic blocks, the clocked behavior, whether in the positive clock edge or the negative clock edge, we have to mention it. And here you can see that it is using an non-blocking assignment. Okay, this we will talk in later. So it triggers only on the rising clock edge, D flip-flop, registers and counters. Edge sensitivity events. So post clock edge 0 to 1, negate clock edge from 1 to 0. So only during that time it triggers. Okay. Now with the reset example, so post edge clock, and then we are adding the post edge reset. Okay. So if the reset it is 0, and then if it is not, it is the signal. Okay. It is something you can call it as a synchronous reset. Okay. Okay. Two times. Blocking assignment is equal to, okay, see the blocking assignment, the syntax is this, equal to this is the blocking assignment. So the execution is, it is sequential within the block. Okay, so if you use a blocking assignment, it will be sequential. So C gets updated value of A. So only after this executes, this will be getting executed. It is not a parallel execution. Okay. So blocking is a sequential execution. Non-blocking assignment update occurs at the end of the time step, maybe in the non-active region. So here it parallelly executes in this block. Okay, and C gets the old value of A. It is not, it will not get updated as soon as, okay, it is not in a sequential, it make it in a parallel way the execution happens. So that is the difference you have to understand between the blocking and the non-blocking assignment statements. Okay, so the execution is immediate in the blocking, and for non-blocking it is scheduled. So usually for the sequential logic it is non-blocking, and for the combinational it is blocking. Is the order dependent? Yes. Here no. So here we will use something like this. Here we will use the clock for the sequential in the non-blocking stuff. Okay. Now in the behavioral modeling, the if else statement is also there. So if condition satisfies, it goes there, or else this statement will get executed. So maybe in the always block, you can have a condition. If A is greater than B, then you can tell maximum is A, or else maximum is B. So this is the thing. Okay, you can use it. So there is a nested if. Okay, A greater than B, C greater than B, D taken care by this. Okay, or else if we want to write it with A comma B comma C and everything, it will not. Okay, that also works, but they're telling that this is preferred way. Okay, this is an preferred way. We can use case statement also, used for multi-way decisions. Okay, so the expression will be executed in this, and according to the expression value, that statement goes, and we have a default statement. So whichever statement is get selected, that will be getting executed, or else the default will go. Okay, and if we write the case, we have to go and write end it. So case, and we have to go and write end case. Okay. Then we have a loop statements, for loop. So integer I, so y equal to 0, 8 times it runs 0 to 7, and we are trying to use it. Okay. Something you have to do it for the repetitive logic and parameterized designs. In all these things, we'll go for it. Maybe this is synthesizable, but while it is not synthesizable, while condition is there, but usually we'll do this in the test benches. So rare in the synthesizable RTL. Okay. This is about the loop statements. Okay. So example, a module, it is a counter module. So we have a clock and reset. We have a clock and reset. So the output is reg type, the counter. Okay. So if the reset is 1, that count is 0, we are putting it in the non-blocking assignment. And if the clock triggers and the reset is, it is not in the post edge, then the counter count plus 1, that is from 0, 1, 2, 3. So since it's a 4-bit counter, it goes to 16, 0, 0, 0, 0 to F, F. I mean 1, 1, 1, 1, 4-bit, no, F. So 0 to F. Okay. So module, end module, begin, and this is the sensitivity list. Since it's a sequential circuit, we go for a non-blocking assignment. And 2:1 multi mux. Okay. So depending on this select line, whether it will give this as an output to Y. Okay. Since we are using this in the always block, okay, it need a reg type. So the begin and the end at, and then star. Then if select pin is 1, then it goes to here this pin, or else we have to make it as the output is given to the A. A simple thing. Okay, the same we can use it with wire type also, continuous assignment. That is different. This is of somewhat different. So the common beginner's mistake using the blocking in the sequential logic. Okay. In the sequential, they will try to go and put the blocking statement, because sequential, it need a parallel. So the preferred is of this non-blocking assignment. And sometimes the sensitivity, if instead of star, they will go and use A. Okay. So we will go and miss some signals. So it is always star for the combinational. Okay. Next, incomplete if statement. Simply if. Then what about the other condition? Okay. But okay, this might be correct, but actually it is not fulfill the exact logic. Okay. So always provide default assignment or else. That is what the things they were telling it. These all are common mistakes when we try to do it in the first. So most modern RTL is written in behavioral modeling. So we use it for finite state machine, data path, controllers, counters, registers, protocol engine, all those things. So the synthesize tools converts behavioral RTL into a behavioral RTL into a synthesize, and then the gate level netlist. So initial always if else case for blocking and non-blocking assignment. Okay. So this will execute once, execute repeatedly, conditional logic, multi-way selection. Okay. Then repetitive logic, blocking assignment and non-blocking assignments. So the behavioral modeling describes the circuit functionality at eye level, use procedural blocks like initial and always, forms the basis for modern RTL design. The golden rule is use blocking for combinational logic, that is always, and use non-blocking for sequential logic. This style is foundation for the ASIC and FPGA RTL development. Okay. So this is what about the today's theory part. Now we will try to move to, okay, the practical part. So let me open the practicals. Behavioral modeling. So new folder, display data flow, behavior. Okay, behavioral modeling. And let me open the terminal. And let me open the other terminal also. Okay, and then let me use this. So okay, so we can see that it's correct. Okay, so now let me create an example, okay, of always dot v. Okay, so let me create an always dot v block. Okay, so this code demonstrates, okay, so the module name is always module. Okay, we having a register, the clock signal is of variable type reg, then initial it execute only once, so the clock is 0, and in the always block we are trying to toggle it for every 5 time units. Okay, then initial begin monitor, it monitors, and we are trying to finish it. Okay, that is the idea. Now I verilog, okay, so 1 underscore then vvp a dot out, so it toggles, okay, and until for this 30 time units. Suppose for example, for the purpose of explanation, let me comment the finish and let me compile it, and then let me run it. You can see that always block runs each, and it goes and toggles for every 5 time units. Okay, and the monitor is getting the things. Okay, okay, so that's why they went and put this finish signal. Okay, so this is about a demonstration of an always block. So it keeps on repeating the things. Since the clock is getting repeated and the monitor monitors, so this is also getting executed. Now we will try an example of an initial block only. Okay, simply only one initial block and we will check what it is happening. Once it's executed, it is not running forever. Okay, now let us try with this monitor and we will check what is happening. Okay, that is also once it is getting executed. Now let us try with the multiple initial blocks. Okay, let us try with the multiple initial blocks. I will create a new file only. Okay, so we have a multiple initial blocks. Okay, so each block will start at 0 time. So we don't know at which order it goes and displays. Okay, we don't know because it is parallel. This initial blocks and these initial blocks execute at 0 time unit. Okay, that is what we learned. So in any order it can come. So it is coming block one. Then again, let me execute it. Yes. Okay, no problem. Since it is of with this small thing. Okay, but it is not guaranteed that it is not guaranteed. Order is not guaranteed. Okay, maybe here it is coming like this, but usually the order is not guaranteed. You cannot tell that always block one executes and block two. No, it is not like that. Okay, so now we will see one example of an if statement. Okay, so we will try to go and look into an if. Okay, for underscore if dot v. Okay, so it is of 8-bit. It is an 8-bit and we are checking the condition. That's it. But uh, okay, since we are not going for much in the hardware level, just to find greater, it is okay. But suppose in the hardware level, select line and not and those things, so we need a else block for the complete module. Okay. Since for this learning purpose, this is okay, no problem. But okay, maybe 4 if and then BVP out. So A is greater. If you change the things, it will not. It will not go. Okay. So since we print like this, we will getting this. Okay. You can use a percentage B or D, and you can print what value is greater and all such kind of things. So this is one of the way of using the if statement. Okay, and then if we use okay else part, okay, and then dollar display b is greater, okay, and then let me change this to 5. Okay, so now the thing is so that's it. This is about the if else. Okay, then if you want to see one example for the nested if, I can show you. So it's not a big deal. For the nested if, okay, so here the mark, depending on the mark, what is the grade are we getting? That's it. What are the grade we are getting? And one more thing, we used equal to, greater than or equal to. Okay. So I Verilog 5, and then let me. So it is in between 50 and 70. I mean 75 and 90. Okay, and it is less than 90 and greater than 75. So we put it here, grade B. Okay, so it is good. If you want to change, you can change and do it. Okay, now we will try to use the combinational logic in the always block, and we will try to use the test bench and test it. Okay, so let me use vim one combinational using the always block. Okay, okay, so we tested it. So it is and behavioral. Okay, in the behavioral modeling, since we are using it in the always, you need a reg variable. Okay, you need a reg type. The output is of reg type. You see that A and B. Now I will create a test bench. Okay, so we want to store the value, so we went and used that as a reg variable, and we are trying to monitor the same as usual. The only thing is we are creating the logic gate using the always block behavioral modeling. Okay, so 6 combinational 6 test bench, and then it works. Okay, okay, it is working. Now I want to check what happens if we comment this. Okay, what happens if we comment it. Okay, So it went and the stops. Okay. Okay, we are not using it in an always. It is in the initial, it runs only once. So no problem. Okay, just for the testing purpose. Okay. So maybe I can show you the mux code, and you can create you the test bench for yourself. Okay. So A, B, select line, and then this is, and then you see that, okay, in the always block, that LHS want to be a reg type. So if you put star, it takes all the signals, and whatever it changes, this always blocks will go and execute. So if this becomes 1, then the output is B, and if it is 0, then output is Y, I mean A. So that is the mux, 2:1 mux. You can write the, because in many program we have written the mux. Okay, so I hope you guys able to write a test bench for that, and you can test it. Okay, then comes the case statement. Case statement case. Okay, we will see one demo for the case. Okay, so this is the case demo. We have a selected line. Depending on the select line, the case goes and executes. So it displays 1 0 1 0. So maybe it goes to the state 2. Okay, so I verilog and then 8, and then let me go and use it. So now it is in the state 2. Okay, so depending on the select line, you can go and choose the state. So maybe it might be useful in the finite state machines. You can have number of state, as much state you can have that value, and when it goes over there, it can switch to that state, this state, such kind of things. You can work with these case statements. Okay, so likewise for the mux, okay, we can use this case statement. It will be of what we'll tell a easy way of understanding. Okay, so here let me go and quit, and then 9 underscore case mux dot v. Okay, so you see that the input vector type is of 4 signal, and to select the 4 signal we need 2 signals as a select line. Okay, so depending on the select line, we can go and choose which as the output. Okay, so it is a mux, because here we don't have a default case. Why? In the sense, because we covered all possibilities of the select line. Okay, maybe we can check for xx or yy, but that is a tri-state thing. But okay, no problem. Okay, so since we are giving the input, so this will be of, yeah, it makes sense. Okay, so because we didn't give display, you can write a test bench for this, and you can write and you can get it. Okay, So this is a design file. We didn't write any test bench. If we need, you can go and write. This is to show that using the case, we can go and write our own. Okay. Now we will go for an for loop. How to use the for loop. Okay. Okay. So it will display it for 0 to 4. It is normal, like if you have seen this in the C language, it is something like C language only. Okay. So I verilog 10, and then you can see that it went and printed the things. Okay. This for loop is synthesizable. So no, nothing. Okay. So if you want to write a sum of the numbers and all those things, you can go and use this for loop. Okay. So now we will try to check the what is happening with the repeated loop. Repeat loop. Repeat is also an procedural. It comes under the procedural block. Okay. So we have used a repeat for 5 times. So I hope it repeats for 5 times. Okay. And here we are making the count, and then we are trying to do it here. Okay. So let me go for an iverilog 11 repeat, and then it went and repeated it for 5 times. Okay. That is what about the repeat. And you can use while loop. You can try by yourself for the while loop. Okay, that is not a big deal, I think so. You can try and take a look for our. Okay, now we will try forever loop. Okay, it is something like an infinite forever. It is not synthesizable. So forever dot v. Okay, so now for our demo, we are using the clock. Okay, clock, and it toggles for each and every 5 delay, and this starts at 0 seconds. This is also starting, and whenever this changes, the monitor will go and look and put the things, and we are waiting it for an 30 time units. If you are not using this, it keeps on toggling it forever. Okay, so that we will do it in the later part. Maybe I think 12 for hour. So up to 30 time unit, you can see that till 30 time unit, and it went and finished it. So now if we go on to use, when we try to comment this, then each and every 5 time unit, this loop will get executed. And then since we use the monitor, it goes and monitor like, okay, you can see the things happening. Okay, so we want to be careful when what are the things we have to use. So that is why it is used only in simulation, because it is not for a hardware synthesizable. Just for simulation purpose they went and used. They are used, will use only for the simulation purpose. Okay, so now the blocking assignment, we will try to understand the block, block, blocking assignment statement. Okay, so this blocking assignment statement, it executes and displays in the active region only, and that too it is sequential. So A is 1, then B will get 1, and C will become B. So the thing is blocking, and you see that it executes one by in a serial way. Okay, and you see the non-blocking assignment. Okay, let us go and use the non-blocking assignment. You will have an idea. Okay, 14 underscore non blocking dot v, non-blocking dot v. Okay, so only simple, we used a non-blocking assignment. Okay, there in the blocking assignment sequentially it goes and executes, but here it is not in a sequential way. Okay, it will be executes at zero time, because it is in the, but the thing is it executes in the inactive region, so it will wait. Okay, so it will not execute in the active region. That is the thing. Okay, so I mean it okay, it might be executing, the state changes happens in the inactive region, it waits for the inactive region. Okay, so if you see Verilog, I mean 14, I think, non-blocking, and you see that all things depending on A only, this B value comes, but these all executed at a parallelly only. So it is a don't care condition. We get a don't care condition, but that is the not case for the blocking assignment. Okay, so this is what you have to understand regarding this. Okay, so using this you can go for the flip flop and then all other things. Okay, those sequential such kind of things. Okay, up down counter, shift registers. Okay, so something like that you can go and do by yourself. Okay, uh, likewise you can go and create a function also, and you can try by yourself, that is not a big deal. Okay, functions and all, maybe I can show you one function example. Okay, okay, so I'm creating a square function. So function, and you have to write end function. Okay, so that square is having an 8 bit, this is the number is 8 bit, so square number into number we are telling, and then in the initial function we are trying to call the square of 5. So what it is going to be. Okay, a simple like a C, like, but not exactly like C, but a similar kind of things. Okay, so 15, and it should get 25, so it's called. Okay, so it's a function and all the things we can go and do it. Okay, I hope you guys able to get an idea. So if you have any doubt, uh, let me know. Okay, please put it in the chat. Okay, Okay, thank you all. See you.